Hello, in this video we begin our discussion of the transition metals. And so we as a department decided we would skip the beginning of this chapter, which is basically transition metal fun facts. And so look through that if you want. We're not going to cover it here. But what we're going to do in this video is we'll start out with, hey, what's a transition metal again? And then how they make complex ions, which is the bulk of the new stuff of this chapter. And we'll talk a little bit about polydentate ligands along the way. Okay, so where are the transition metals? Here they are. You know where they are. Okay. Now, we're interested in electron configurations, and this is from the first semester of Gen Chem, is that the electron configurations of metals and metal ions are different. And so metals are roughly as you would expect, at least in the first row here, right? You have the 2 electrons from the 4s, which are these 2 over here, and then you have however many 3d electrons you have based on the metal. As you go down a little lower, it gets kind of weird. So generally I care about the trend here and not the specifics, a little farther down. Then there are here 2 exceptions I want you to know for the first row stuff, is that chromium and copper both take an electron out of the S and put it into the D to make filled or half-filled D subshells. And so if you look at chromium, right, if it puts one more electron into the D, it looks like manganese, which has 5d electrons, and filling this halfway is better than having 2 in the 4s. And the same is true with copper. Filling it all the way is better than having 2 in the 4s. But if you look at nickel, filling D all the way is not better than only having 0 in the 4s. So there's kind of a limit to that. But that, again, is something that hopefully you covered in the first semester of Gen Chem. If not, just know that exception and you're fine. Okay, now metal ions. So here's cobalt, kind of somewhat randomly chosen as my example here. And if you look at the metal, well, you fill the 4s first because it's lower in energy, and then you put the rest of the electrons into the 3d. Now when you make the cobalt ion, the D subshell is now lower than the S. So as you fill from bottom to top, you're going to fill the D first, and then the S will remain unfilled. And so this is true for any transition metal ion, is you fill the D, and you pretty much never fill the S. And so the cobalt ion is now a 3+, so that means it has 3 less electrons over here than you had on the left, because you lost 3 electrons to make the ion. So another way to say this is that first row transition metal ions do not have S electrons. That kind of rephrases what we just said. And so let's look at a couple examples. We're trying to look at vanadium, which is down here. And based on its position in the periodic table, you're going to fill the 2 S electrons that are represented by potassium and calcium. You fill those first, and then you start stuffing things into the D. And it turns out that potassium is the 4S that fills last there. And then you start filling the 3D. And you can put the little brackets in to say, okay, if you start with argon, the last transition metal, here's what you do after that. Now, when you take 2 electrons away, well, first of all, there's 2 less electrons total. And then, like we just said, you don't have the electrons in the 4s. So the thorough way to think of it is that when you make an ion, the 4s electrons dump into the 3d, and then you start taking the electrons out of the 3d. And if you have vanadium 3+, well then you only have 2 in the 3d. And so we actually use this number of electrons in D as a characterization of the type of transition metal ion. And so we'll write D3 or D2 to illustrate that, right? So we can call vanadium 2+ a D3 ion because there's 3 D electrons. And then vanadium 3+ is a D2 ion, so on and so forth. Because these categories, D3, D2, they affect what it looks like when we start dealing with crystal field theory in the later parts of this chapter. And then don't forget the D orbitals have these kind of shapes. You've seen them before. They do tend to affect the chemistry in a big way, especially when we get into crystal field theory. So keep that in mind. Okay, so here's the new idea in this chapter that is the thing that we then talk about for pretty much the whole chapter. Transition metal coordination compounds, also known as coordination complexes or complex ions, because usually they're an ion of some sort. And so what this is that, say you have your metal, and then it'll bind to these things called ligands. So here's the metal, here's the ligands. And this bond here is mostly covalent. Covalent to ionic is actually kind of a sliding scale, and this is somewhere in the middle-ish, right? It's not pure covalent like it would be between nonmetals, and so therefore it is susceptible to substitution reactions where you swap ligands. But, it's not ionic. It's not held together by just charge. So it's generally considered a covalent bond that's kind of weaker. And so these ligands stick to the metal and form this coordination complex, or this complex ion. And now, if this thing is an ion and it has a charge, well, you need to have some other ion to balance that charge, right? You can't just have potassium. You got to have potassium chloride or something to make the charges work. So this is no exception. And so then this thing in the brackets is the complex ion. And we do definitely use these brackets, right? If you're going to write this, you put the square brackets in, and everything inside it is what's in your complex ion, this piece. And then everything outside it is the counter ion. So, okay, I already talked about the metal-ligand bond being mostly covalent. In contrast, the bond between the complex ion and the counter ion is a normal ionic bond, just like every day. And when you put this in solution, they'll dissociate, right? Your metal-ligand compound will generally stay together, and then you have your counter ions floating away. An exception here is water functions like a very good ligand, and in some cases it might displace the ligands you already have on here, but that's another story. Turns out it generally doesn't displace the amine ligand. Okay. Something else to introduce is coordination number, and this is the number of bonds from the metal ion to the ligands, and generally 2, 4, or 6, an even number. There's some exceptions to this. And if you have ligands that only make one bond to the metal, then the coordination number is just the number of ligands. You'll see that there are ligands that make more than one bond to the metal, and then you're counting the number of bonds. So you would double count a ligand that binds to the metal twice. So it's a number of bonds. Because this affects the geometry. Just like we did in VSEPR, valence shell electron pair repulsion, the number of things attached to the central atom leads to the geometry. So if you have 2 things, it's linear. If you have 4 things, it can be tetrahedral or square planar. And if you have 6 things, it's going to be octahedral, right? Named octahedral because there's 8 faces if you were to shrink wrap that thing. Okay, so that's coordination number. So when you have these ligands that only bind to the metal once, that's pretty straightforward. You look inside the brackets to find the coordination number. All right, there's 5 of these amine ligands, and then there's 1 chlorine, so that makes 6. And then the Cl2 out here is the counter ion. You don't count that because it's not in the coordination complex. You can write this without the counter ion, then you just say, hey, this whole thing is 2+, and then this is still the same story. You have a coordination number of 6. And then for the last one, if you had 4 aqua ligands, they're called, 4 waters on here, then, well, the coordination number is just 4. Now, a little more about ligands is the ligand needs to be a Lewis base. And so if you remember, a Lewis acid will accept a pair of electrons, whereas a Lewis base will donate a pair of electrons. And so our ligands need to have this lone pair of electron that they can donate because the electrons in this bond, right, each bond is 2 electrons, they don't come from the metal. The metal doesn't give them up. And so your ligand needs to bring its own electron pair to make this bond. So, requirement to be a ligand, it has to have something with a lone pair of electrons. And then you make this coordinate covalent bond, right? You can call it a covalent bond, but it is good to have some sort of, flag or caveat in front of it to say, it's a coordinate covalent bond. All right, so now let's look at some types of ligands. So these ligands that make one bond to the metal atom, they're called monodentate. And this literally is one tooth in that it bites the metal ion in one spot. And so, there's quite a lot of these. And we divide them into neutral ligands and anionic ligands. And the neutral ligands won't affect the charge. So if your metal ion is 3+, then your complex ion is also 3+. Whereas these anionic ligands, say you have a 3+ metal, and then you have 6 fluoroligands on it, so then your overall charge is -3. They will add into the charge on this complex ion, and we'll talk about that in a minute. Now, also the ligands, they each have their own name, and so it'd be like, your Clark Kent, or this is what you go by. Normally, you go by ammonia, normally. But when you're a superhero, or when you're a ligand, you have your special name, right? So And ammonia has the ligand name of amine, and this is, I think, one of the very few times in chemistry that we spell amine with 2 M's. It's just that special. I mean, this is water. We call it the aqua ligand. This is carbon monoxide. As a ligand, we call it the carbonyl ligand, right? This is one of my favorite ones, carbonato. And, various names for these ligands. Now, other thing is they can bind through different atoms. So in this table, they're underlined based on which atom binds to the metal. And, historically, this was obviously a subject of much debate as to how they actually bind. And so it has to have a lone pair on it. And then in some compounds, these will both have lone pairs on it, but it will only bind through the nitrogen. In other compounds, like the thiocyanate ligand, both the sulfur and the nitrogen have lone pairs, and it can bind through either one. And different metals will have preferences for which one of these will bind. You could conceivably have a metal where it binds, with equal efficiency from either atom, and then you have a mix of how they bind, and that would affect some properties. And yeah, so here's our list of ligands. You'll generally get the names and the charges of ligands in my class on the test, but you definitely need to know how to work with them, and that's important. And then, you should just memorize the common ones. We use amine and aqua all the time. Just memorize that. It'll make your life easier, honestly. All right, so you can have bidentate ligands. They have 2 teeth, and so they bite to the metal ion in 2 places. And your textbook puts this kind of in a different section, but I'll put this idea here. And so these are in a broader category called chelating ligands. Chelating means claw, so it claws around the metal ion and wraps it up in a number of different spots. And they're also broadly called polydentate ligands, right? So polydentate ligands are chelating ligands. When it only goes in 2 spots, that's bidentate. So oxalate and ethylene diamine are very common examples of bidentate ligands. And the oxalate will bind through these oxygen atoms. Sure, this thing resonates, but once it binds, it stops resonating, so we can draw it in a single form. And we give this its nickname of ox, and then we'll say that it's a -2 ligand. And then ethylene diamine gets the name En, and it binds through these nitrogen atoms. And the number of carbons in this little spacer here are enough such that it can wrap around and bind in the metal in 2 spots where the metal wants it, usually along some sort of either tetrahedral or more commonly octahedral geometry. And so these can wrap around and bind 90 degrees from each other. If you had just 1 carbon here, I don't think it would work. If you have more carbons, then it just gets kind of floppy. All right, so here's some of the polydentate ligands, right? If it's got 3 places it binds, tridentate, tetradentate. You could call this hexadentate, but I've never heard anybody say that. So some examples here. We use EDTA a lot. It's in consumer products. It does a great job of chelating metals. And then, in your consumer product, it'll chelate the metal, and then it's never going to come off in any reasonable circumstances. And so then that would prevent your metal from doing whatever it might do that you don't want it to do. So that's EDTA. It can bind through these orange atoms in these different spots. It's called ethylene diamine tetraacetate. You can work out how that makes sense if you want. I wrote it here with spaces, but we generally don't write it with spaces. You just jam it all together. Ethylene diamine tetraacetate. And then you sound cool to all your friends. Biologically, this one's important. So heme is in hemoglobin. It's what carries the oxygen around in your bodies. The oxygen coordinates to the iron, which is then coordinated to this molecule called a porphyrin. And these 4 spots here that are in blue are the nitrogens with lone pairs that then make the coordinate covalent bond to the iron. Then your oxygen comes in on the top, something else can come in on the bottom, and then that's how it binds. So you can look at chelating ligands in 3D, and I think it makes more sense. So I took this figure from Macquarie, and I like it. It shows that these things really do wrap around, right? EDTA just wraps all the way around your metal. And then in a bidentate thing, each one of these will kind of wrap around and occupy spots that are 90 degrees away from each other on the octahedral geometry. And then these will bind in different ways, right? If you look at them, it seems like the propellers are going in the opposite direction, if you will. And then that matters, and we have terminology for that we'll get to later in the chapter. All right, last thing in this video, and I kind of hinted at this before, since this metal-ligand bond is not all the way covalent, you can substitute ligands pretty readily, and there's a preference order here that has to do with binding constants and things like that. But generally, say you take copper with the 4 aqua ligands, and that starts out as green. If you dump some ammonia in there, the ammonia will replace it, and then you'll have copper with 4 amine ligands, and that changes color. At the end of the chapter, we'll tell you why. And then it also drops the water off to rejoin solution. And then you can keep going. You can add ethylene diamine, and that'll kick off the amine ligands, and it will bind, and so on and so forth. So these ligand substitution reactions can occur quite readily. All right, thanks for watching.